We're going to make the stream pretty quick. We want to stub in the basics of the rendering algorithm, because we have some code and it's working, and all the foundations we've written they're in place now, I think, or so I think. We'll find out as we go here. But let's take this function here, covPix to covBits, canvas user pixel location to canvas user bits, this function here. And we want to call this 3 times, right? So there's 3 different layers that can be overlaid over each other. And we only want to select from the active offset. So let's kind of hard code this call into some code somewhere for the shader code. And we'll figure out the particulars about we'll figure out the particulars of how this needs to go later. But right now, let's just stub this in and get this working, right? So these are all int32s. We have this cov.ix, cov.iy. So we know this is like that. And we know that the layer index, we're just going to hard code the layer index, and we're going to hard code the offset index to 0. And then what we're going to do is we're going to hard code some more stuff, and we're just gonna get this working, right? So we're gonna just do whatever we have to do to get this working. And so the first step, I think, is to be able to use this function 3 times. So I think the first part is, before we even try to use it 3 times, let's just see if we can use it 4 times, right? Just if we can throw it into here, can we get it to compile? Can we get the shader to compile? All that good stuff. So let's delete the shader here from here so we can rebuild it. And then rebuild the project and see if that introduces any type of monkey wrench in our code, or if this actually goes off without a hitch. So far, looking good. And now let's go to the shader code. So shader code does not indicate any type of syntax error, so that's awesome. So now the next thing is, okay, we want to call this 3 times. So let's just cut and paste this 3 times. And we want to use layers 0, 1, and 2, right? So we want to use all the layers because we want to collect all of the pixels on all of the tiles for all of the different layers. And so now let's just give that a run, right? So let's delete the shader again. And then rebuild everything and see, hey, can we get this working? And if we can get that working, then we can start to write our blending algorithm to blend all of the different tiles together and get something on screen that isn't as boring as this, right? And then we'll still need to do like camera controls and whatnot and all that nonsense, but we're getting somewhere. Okay. So we're going to get some bits. We know that this function returns a uint32. So we need u32 I'm thinking u32 L1 for layer 1, maybe, right? And then we could do that for layer 1, layer 2, layer 3, right? So paste and paste. So u32 L0, sorry, L0, layer 0, layer 1, and layer 2, right? And then this index here, the layer index is 0, 1, and 2, like that, right? And we just want to see if that works, right? Does that work, or does that not compile, right? So as I do more of this, maybe I'll have more confidence in the build system. But right now, I'm not super confident in this, so that's why I'm kind of like doing in small pieces. Unused variable, yes. This is unused variable. They are correct. So now the question is, how are we gonna, so we have to write some more code to get this to work, right? So I'm thinking we do like, we red, green, and blue layers, right? Like the layer 0 is going to be a background, and it's going to be we're doing back to front, I think. I think I've decided on back to front, though it's like I have so much code everywhere that it's like maybe I didn't. Yeah, back to front because 0 is always the backmost, then we layer on top. I think that's how we kind of decided to go with that. So that way, layer 0 is always the backmost layer. I guess you could always do something where layer 0 is always the frontmost, and you could work further and further back. But I think that if we did a front to back renderer, we could have a lot of optimizations where we use like occlusion to render more efficiently. However, the problem with that is we're using OpenGL, we're using Glsl shaders. We're not really using something that's if we were using OpenCL, that would be great, but we're not using OpenCL. And if we render front to back, you know, well, then I think it's easier to think in terms of transparency, right? We render the thing in the backmost, and then we render something on top of that, and on top of that, and on top of that, and it's going to be more friendly to transparency. So I think we should just try to get the optimum performance to where if all the materials are transparent, can our engine still kind of chug along fast, right? Like a lot of engines, when you make everything transparent, it just crashes on you. Not crashes, but it lags, right? It takes up, right? A lot of engines cannot handle transparencies. So maybe we should go back to front, I think. We may change our mind. But I think right now 0 for the backmost layer just makes sense. Now, maybe there's a reason not to do that. What do we think here? I don't know. I don't know what to think. I don't like it being completely arbitrary. I think a lot of this is just going to happen based on trial and error. So, what are we doing here? We're trying to get a final pixel. And right now we're using this thing here. But what if we took let's do a U32 U32 oh no, UN32 pixel. Though sometimes we use that to mean a pixel array. But let's just say U32 pix equals, and then just kind of shove something in here, right? So we could just finish this, right? So if we really want to get this working, well, we know that we have this kind of like 2-bit color. We have like 0, 1, 2, and 3. So what we could do is we could say let's just do something really simple for now. If we we're just going to take we're going to take a uint 000, And we're going to combine it with... let's assume that U32 L0 shift 16 U32 L1 shift 8 U32 L2 shift actually we should do 8 16 and 24. And I don't know, like, we're not really gonna solve the rendering problem here. We just want to get this to not be a used variable and then figure out the exact logic later. But right here, then we want this to be like just a uint FFF, right? So UFF, uint FF, right? And we'll shift that over 0. Now, we don't have a thing called UF yet, so we need to make that. So wherever this is defined, we're going to define something similar. So we got U00I00. It'd be nice to create a UFF. So U00, I don't know where we're going to put it. I guess we could put it like right here. Undef UF, right? And then we can, because we got to make sure not to get any like integer conversion errors, so we have to be careful about how we use unsigned variables in our code. Otherwise we get like implicit conversion errors. And yeah, so we'll put UF over UU or U00. So let's just duplicate this and call this UF. And this is the Glsl code. So we just want like a uint 0xFF, right? So that's how we're going to do this one. We could also move this up like that. Then we can take these numbers here, move them up, shift them up. Because now we have one more thing. So UF is beneath Sam, right? So beneath Sam, we're going to put UF. So right here, we're going to duplicate this. We're going to put UF for uint FF. And this is C99 code. So for C99 code, we can just go 0. You can just go 0xFF. No problems there, right? That's just going to work out of the box. No issues with that. So this is 15, 16, and this is 17, and then this line down here is 18, and this is 18 as well. So that makes sense. Okay. So now let's look for where UF is defined. We got UF as uint cast or uint constructor with 0xFF, and then if it's C99 code, we just use the literal 0xFF with no casting around it, because that'll work fine. And then over here, that looks good. Now the other thing is that this is unused, right? So we still have to use this somewhere. And I think that one way we could do it is, I'm noticing we have all these kind of, we're trying to get all these colors, right? We're trying to get all these colors or whatnot. The idea is that we're going to create some type of pixel, and then later we're going to extract everything. So even though this might look a little bit convoluted right now, let's not worry about it. So U32, let's call this UVEC4 pic. So we have a U32 pixel, and now we have a UVEC4 pixel. And that is going to equal nothing. Because we're going to we gotta write it in a way where where it works as GLSL and C99 at the same time. But yeah, so dot x is going to equal, going to take the U32 pixel, right? You're going to take the U32 pixel, and we're going to take the U32 pixel, and we're going to shift out RGBA, right? RGBA, so 24. We also need to mask it, right? And UF, right? We got our little UF thing for that. So X, Y, Z, W, 24, 16, 8, and 0. And then once we have this kind of unpacked from here, right? So we're taking this that was packed together, right? And we're going to have more logic for how we do this, right? But right now we just want to stub something in. And then we're going to take it, we're going to take this U32, and then we're going to unpack it. This is kind of inefficient, but we just want to get the basic logic working first, like make a skeleton for what we want to do. And then once we have this UVec4 thing, well, UVec4 P5D, we can just take the UVec4 P5D thing here. Now it's just a Glsl fetch, and now we can replace UVec4 P5D here with the UVec4 Pix, right? So we're just going to say UVec4 Pix, and all we're doing is we're normalizing it, right? So it's some type of RGBA. This is some type of RGBA pixel, and we want to turn it into a normalized color, right? Like a normalized in terms of how like OpenGL works with color in the range of 0.0 to 1.0. So we'll do this. And we'll leave alpha as 1.0. Yeah, so we're not going to worry about this alpha value here, right here. We'd have to do some weird alpha compositing anyways. And we'll just see if this works. And we'll see if this compiles. And if it compiles, then we'll see if the shader compiles. So we'll see, first of all, if the project compiles, and then see if it also compiles as Glsl. So first of all, we have some type of problem with... yeah, so... this is not correct. We want to put the OR over here, right? So our bitwise OR. So we're taking this and we're kind of bitwise ORing it. Taking these different U32 values and we're just shifting them over. Now this depends on, this is kind of assuming that all these U32 values are, these U32 values are actually going to be, well, they're UNT32 values, so this is kind of, this operation here is nonsense. This operation is nonsense. Just a placeholder piece of logic for now. Yeah, so this is complete nonsense. This right here is complete nonsense, and we're going to fix it eventually. So, we're on video 118, and the time is 0 minutes, 18 minutes, 23 seconds. Yeah, so we, right now, at this time in the video, we have written this complete nonsense right here. And we're going to eventually rewrite it in a way that is not nonsense, but we just want something to get on screen that we can work with and something that we can compile, and then we'll worry about fixing this logic up, right? So we're taking, we're getting all of the tile values for layer 0, all the tile values for layer 1, all the tile layers for layer 2, right? For all these different layers, and they're all bit packed into a UNT32, and then we have to extract them and palletize their colors, and then blend the layers together, and do a lot of fancy blending to really get this to work. So this is absolutely not what we want, but it's good enough for now just to stub something in to try to get something to compile. So, first step, can we compile? Okay, we're compiling. The second step is, will the shader code compile? So let's take a look at this. So the shader code did compile. Now it's kind of how do you say, uneventful. So it has turned kind of like half white, half black. Now, I don't know what I expected to see because I gave it like a very nonsensical algorithm. And so we might want to think about, well, how can we use what we already have to create something less nonsensical? Well, I think rather than thinking about, oh, how can we create something less nonsensical, let's actually think about the final algorithm for how we actually need to do all of this. Now, it doesn't have to be efficient, it just needs to be logically the correct way to do this. We can worry about efficiency once we have something, you know? So really what we want to do is for every single layer, we want to alpha blend. If it exists on a certain layer, we just want to alpha blend it and not worry about its order. So for layer 0, if we shift over 0 bits and then we mask it, so and we mask it with a B3. Do we have a B3 or a B03? Do we have a B03 something or other? No, I know we have something like this. Let's look at where UF is and see if we have some type of binary value for that. B3 is yeah, B3 for binary 3, right? You went 3, and then here it's just a 3, right? And so B3 stands for binary 3, and we can use that to create the masks, right? So B3 binary 3. I don't know why we have B3. Why not like B111, right? Like, that would make more sense. In fact, if we do not have a thing called B11, then I am going to make a define for that, yeah. Because B3 seems kind of nonsensical. I don't know why I named it B3, but we're not going to worry about refactoring. We're just going to add on this B11 here. And worry about fixing that up later. But yeah, but we just want like binary and it's 1, 1, right? And we have enough room to actually do that in the 3 characters that are provided, so why not, right? So we got 19 things here, and we're gonna put the B11 underneath the B3, and B3 and B11 are actually exactly the same values. So D, and we're gonna make this B11. It's gonna be a 3 here, and this is 15. This is 16, 17, and this is 18, and for a 19 total, right? 19 total. Yep, 19 total. Cool. So now let's go through here and say, hey. Now, we're going to be able to mask this with the binary 1, 1, right? So binary 1, 1, if we want to look for where that is in this shader, it's only in these 2 places right here. Also, we need to undef this, right? So if we define this, then we need to undef it as well. So let's, do we undef UF as well, or do we have to add that as well? Looks like we forgot to, oh no, we didn't. Undef UF, and then down here, where we do B3, and then we do B11, right? And so let's take this, and now we got 19 undefs. 11, 12, 13, 14, 15, 16, 17, 18, and 19. 19 undefs. Okay. Let's go look for B11 again. So here it is declared, and here's where we're using it. So we just want to extract the smallest tile value, or the... yeah, smallest tile value? Yeah, tile exponent 0, yeah. And we just want to take this and we want to multiply it with some type of color value, really. But before we multiply it with a color value, we want to, what do we want to do here? We can multiply it with a color value, we could turn it into a percentage first, or we could, I don't know what we want to do. So if we take, so 0, 1, 2, and 3, so 3, we take 255 and divide it by 3, what do we get? So 255 divided by 3, really quick. We get like 85. So 85 to hex, 0x55. So we could take this and we could multiply it by 0x55, and we could get something where if it's 0, we get 0. If it's 1, we get something more intense. If it's 2, we get something more intense. If it's 3, we get something more intense. We could get some type of gradient in terms of the color channel value. So why not something like that? So times we'll say hex 55. I mean, we're going to have just a lot of weird stuff, right? We're going to call it hex 55 for now. We're just going to we're going to keep on just shoving things in here, right? So we're going to call this hex 55, right? Because that's what it is. Right? Because I don't want to deal with random conversion things and whatnot. So we're just going to put them here, right? So we're going to go duplicate this. We're going to create hex 55. And it's going to be a uint of 0x55, right? It's hex 55, not decimal 55, right? And then beneath, so it's beneath B11, right? So we could go down here and go Control D, and we could create another thing called H55 for hex 55. And this can just be a normal kind of hexadecimal number, so 0x55, with nothing kind of fancy surrounding it. And then we can renumber this 15, 16, 17, 18, and 19. And this last one down here will be 20. That checks out. So hex 55. So we got hex 55. And hex 55 is undefined down here. So that looks good. So we're just going to take the current tile and we're just going to multiply it by that, and that'll give us a value that is kind of in the like 0 to 255 range. Not perfectly in the 0 to 255 range, but good enough. And the next thing we could do is we could just say that this color is like, how do we want to do the colors for this, right? How do we make colors? So if we really want this to work, we could do so we want to multiply it by, let's assume that all of the tile values are, I don't know, we need some type of palette. We need some type of default palette. Right? I think if we don't have a default palette, then we're going to be confused here. So we want to define how all the tile sizes are the same color, and then we have like a red. We have red, green, and blue layers, right? Red, green, and blue layers. Let's not make this too complicated, right? So we multiply by this because this gets in this like 0 to 255 range. And then And then, what do we do? Well, if this is just the red channel, if we just want to say this is the red channel, then what we could do is we could take this and say, hey, this is the red channel, and we could just, so 2, 4, 6, 2, 4, 6, 7, 8, 9, and 10, 11, and 12, 1, 2, 3, 4, 5, 6, 7, 8. So this should be the last one here. And 14, right? So these are all the different tile size exponents that are packed into this layer here. And we're going to mask it with 2 bits to get a 2-bit color, and then we're going to map it to, we're going to multiply that, we're going to create a palletized color intensity, right? So, roughly, the values 0, 1, 2, and 3 will be evenly spaced, incremental different luminosities, right? And we'll just say that these are all red pixels. And so what we'll do is we'll just kind of like add these all together, right? So we'll just do like, you know, a 0 with a plus, like this, right? We'll just smash this all together. And once we've smashed it all together, all we got to do is divide by 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So we divide by 8. And we get a bit value. We get a byte value, right? Now this is... These are okay here, but we gotta avoid accidental implicit cast problems. This is a hex value, which makes it a uint value, right? So if we look at where we're declaring this, right, it is a uint 0x whatever the heck, right? So all these are uints. This is a U32. This is a uint binary. Right, so that means that this needs to be U00, so U00, so uint 00, and then we want to divide by, 8, but we don't want to make any mistakes here. So we should have like something called U32 make and 8, right? So U32 make with an 8 to get the proper casting, right? So, it doesn't look like I can find that. Is it because we have F32 Mac? Like, what's the deal here? We got F32 Mac, but we don't got U32 Mac? What the heck? So, you know, we think we got all the polyfills we need, and then as we start coding, we're like, nope, we don't have all the polyfills we need. And I just don't want to keep on making a whole bunch of different macros like this. So, we're going to go open up the polyfills file. So, polyogl, right? And we're going to open up the functions file here. We're going to look for the macros and see what kind of makes we have for making different bit width types. So we got make floatvec4, we got make ivec2. So I already see a problem here. We got make this, then we have ivec2 make, right? This is inverted. This is inverted. That's bad. None of that. Is this the only one where we kind of screwed that up? Did we, like, do everything correctly, and then, for whatever reason, we're like, hey, this thing, let's, name that wrong. Is it because we're not using it anywhere? Is that why? Is that why we don't see that consistency? Let's find it in files really quick. And, that's ridiculous. So, IV2 make, whatever make, so we really should change that around, right? Like, the make is the make part is the generic part, this is the more general part, this is obviously the more specific part, so that is not how we should word that at all. So copy this for a second, and then we're just going to say make IV2, make ivec2, So polyogl make ivec2, find in files, find all. Not too many places. Polyogl. Okay, replace in files. Okay. So we need to fix our stupid naming conventions here. So we have, do we have a make I32? We got a make I32, we just don't have a make U32, right? So if we look in here, we don't have a make U32. So let's do that and also figure out what the heck is going on here. So we have this GLSL polyfill, but we don't have the closing section on this. So it's just, we just did a whole bunch of stupid stuff. So make ivec2, make int32. So we got int32, ivec32, whatever the heck. Let's just do right here. Let's just copy this int32 thing. Copy that. Let's paste it here. And then we'll just call this, hey, this is going to be U32 now. In fact, anywhere we see I32 here, we're going to change the I32 to a U32, right? So simple, kind of find and replace. U32. This is a U32. This is also a U32. Now the thing is that how are we using this? How are we going to use this? Do you want to reload it? Yes. So if we look at the use case for this, we really want this one, and this is kind of like, this is where it's going to get us in trouble eventually, but let's not worry about that. This is taking an integer and turning it into unsigned. Yeah, we're never going to take a float and turn it into unsigned. We're never going to do that kind of nonsense. So we're going to make these kind of functions for our specific use cases. Yeah, we would never do that. That's nonsense. So it does make sense for the input type to be an int32, right? So we take an int32. So we're taking an int32. So we're taking a signed int32 bit right here. And we're converting it to a U32, right? So U32. So let's look at this. So U32 and int32. So we're taking the orange and turning it into cyan, right? So here's our orange. We do a little cast on the orange to turn it into cyan. Here's the cyan comes out. So the orange comes in, cyan comes out. And we can see that the flow of the colors makes sense there. Okay, cool. So now that we have that, let's go find in here where we're making these macros. And we need to completely change how we're doing this. But before we do that, let's just... we wanted to put this one above the ivec2, so we wanted to put it like right in here. So define, and let's just do it the correct way. U32 make. Oh, I see why. No, make U32. Make U32, right? And then put that here, right? Because then the right, when I highlight this, it actually matches. But when I highlight this, it doesn't match the function, right? It's like, why would I do that? That's not consistent at all. Anyways, let's kind of fix the let's get this working first, and let's address the inconsistencies there in our code, our horrible inconsistencies. So U32. So for a U32, it's going to be uint, right? So instead of int32 make, this is U32 make. So uint, right? Simple as that. And then we want to say, hey, do we have that anywhere? So it's just here. And then we actually want to use it, right? We actually want to use this. So down at the bottom, where we're kind of writing this crazy code, we have like that 8. I'm going to call it make uint32. So we're going to take this, and we're going to just add all of these different values in the range of 0 to 255, right? So we use this hexadecimal 55 because we know the range. 0 to 3 times hexadecimal 55 gets us something less than 255, less than or equal to 255. We're going to take all these different byte values, and we're going to composite them together, right, by just doing a simple little average, right? And the average right here, we just divide by, 8, right? And then we have a final luminosity value, right? So we're just going to say that the first layer is just red, right? So red, green, blue, like just keep it dead simple. And so now, in order to get this working, we're just going to take this nonsense, right? We're going to take it, and we're going to put one more set of parentheses around here really quick, so that we can take this and go like this. We can just duplicate this nonsense, this craziness. And we just want to add these together. Or actually, we don't want to add these together. What do we want to do here? We want to take, well, first of all, this is going to be layer 1, and this is going to be layer 2, right? So we're going to change the layer that we're getting this from. And so this is our red layer, green layer, and blue layer. And then what we want to do is, since they're the individual color layers, we don't actually have to see any feedback. We don't actually have to do any fancy blending besides that, right? So we can just say that this U32 pixel is just, like, we don't even need U32 pixel right now, right? But because we want to kind of keep to this kind of workflow, because eventually we may need this workflow, we're going to say that, we're going to comment this U32 pixel out really quick. And we're going to say U32 pix equals U00, like a U00, or it can be this value that should be in the 0 to 255 range. And we're going to shift it over by 24. We're going to shift it over by 24. We're going to put another set of parentheses around it. And then we're just going to OR all this craziness together, right? So we're just going to say, like, so we could say, like, OR, and then put, like, a OR here, right? I think. And then we can triple this up as well. And then we can take this right here, this nonsense, and we can take that and say, shift that over 16, right? Pack that into the green channel. And then we can put another OR right here. And then we can take this stuff here, put another parenthesis on that as well. And then we can shift this over. So we have 24, 16, and 8, right? And as far as the alpha channel, we're not even worrying about that right now, right? I mean, we are shifting it out here, but we can just say that if we really want to unpack the alpha, like we want to use the alpha in this pixel as well, then we can just take, like, UF, right? Our FF, unsigned FF, whatever. And we can say, it's called UF, right? We call it UF. Maybe we should call it HFF, but whatever, this is what we have. And we're going to just shift that over 0, right? And now everything's nicely kind of bit packed together. And we have this master UINT32 pixel value, right? And this is just ridiculous, right? This is crazy. This is crazy. And then we're going to unpack it, right? We're going to pack it all together, then we're going to unpack it, which is completely inefficient. But the idea is that we just want some type of rendering method where we can verify we want to verify everything is working structurally, right? So we just want some type of basic rendering method that we have a red layer, a green layer, and a blue layer for the respective layers that we can draw on for a given offset, and we just want to make sure that we can actually see those layers and when we render to the screen. So this is quite ridiculous, but it's just what we need to do we just want to get things working first, right? Before we even worry about the little details, we want to get things working. So let's run this. and see, maybe we screwed, I don't know, let's see if we screwed up any syntax, because oh, I'm very surprised. Now let's see if the shader runs, because there's a lot of code in here, and I'll be surprised if I got everything correct in terms of the translation. So that doesn't look like what I think it should look like. I think did we forget to delete the... So this pixel is right here. And we shift it out and mask it, right? We shift out the different values and mask them. And then later we take these values, we make them into... we make them into float 32s, that's okay. And then we divide them to normalize them. And we just forget about the z value, we don't care. So this, or not the z value, but the w value, we don't care. Now that looks right. That looks right. So where are we going wrong here? So U4 pix, we take the U32 pixel, and the U32 pixel is made from here. That all looks about good. I'm thinking maybe I forgot to... Did I forget to delete this? Did I not delete this? I thought I did. Okay, let's delete that, and then let's run this, because maybe I just forgot. Because it looks the same as last time. I highly doubt that we did all this nonsense and that just looks the same. But maybe. Maybe we're just totally... Well, that is... Oh, you know what? This is, we haven't loaded our pattern in yet, right? We still gotta press the P key, right? Because this is just this is what it looks like if we render a checker pattern over every single pixel in the texture memory that's storing the tile map. And, since a checkerboard is kind of completely symmetrical or completely... right, we see the symmetry where there's half white, half black, and we used a checker pattern. Okay, let's press the P key, proof of, what do you call it? P key for, what do you call it? Just press the P key. Okay, nice. So, not exactly what I wanted. It is really close to what I wanted to see. But for whatever reason, it's not... It's like rendering... It's rendering this quadrant over here, but then it's not rendering anything over here. So why is that? Well, the test pattern we used... Is the test pattern we used nonsense? God, that's so close. Oh man, that looks good. That looks... pretty good. Like, I didn't expect it to look that good. So what's going on here? Like, why is this not how we want it to be? So it like renders here. It renders in the first one, but then it doesn't render in the other one. So let's actually hit O for output and save that output for a second. And let's actually look at the mod folder and look at the actual data. So this test file is supposedly this test file sets one tile of every single tile type around the borders, right? Because that's why we see every single data partition here has a 1 pixel outline. So I think this data looks correct, but the other problem is that it's not quite correct, is it? Because this test pattern is... This test pattern, I don't think, is all layers, right? So if you look at this, this test pattern doesn't hit all layers, right? If this test pattern hit every single layer, right? If this test pattern hit every single layer, then we wouldn't have these different gradations, right? It would all be solid white. So that's actually what we're missing. It's not the... I don't think it's the rendering logic. It's just that what we've done here just is not... yeah, what we've done here is not the test pattern we want. We want a different test pattern. So we're close. And if we look at this a little bit, yeah, now that I see this, it does actually make sense, right? So, yeah, I think the rendering logic is actually correct. I think it's just that we need a different test pattern that makes more sense for what we're trying to do. Because this is not the test pattern we want to use. So I am a little bit tired though. So I'm happy. I am happy that we're getting something. So we're finally. So before we close up shop, I'm just sick of this. We should change we should change our defines in here, right? So we have this kind of nonsense where we're like, oh, all these make functions are going to be i32 make, whatever the heck make. Bad move. Bad move. i32 make, you need to be make i32. And let's find in file. Let's see if we find all. Yeah, anything that is... Yeah, any of this nonsense here, we're just going to... we're going to change this. So we did a little quick search, and it looks all okay. So we're going to replace in file. So i32 make is going to become make i32, right? General to specific. Replace in files. Okay. Okay. Now let's search for this iv2 make. Right? So let's search in files for this. And iv2 make is going to be make iv2. So iv2 make to make iv2. So we're going to find all really quick and make sure that nothing looks kind of like surprising, right? And then we're just going to go, hey, find in files. We're going to find this iv2 make. And we're going to convert it to, we're going to find iv2 make, we're going to convert it to this. So iv2 make to this. So replace in files, hold on. Replace in files, okay. Yes. So now we have this fv4 make, so we're going to do the same thing there. So we're going to look for fv4 make, and we're going to replace it with make fv4. And let's find all really quick. Anything surprising? I don't see anything that jumps out at me as surprising. So let's take that. fv4 make is going to be make fv4. So find in files, replace in files. Okay. Okay. And then the last one is this f32 make. So let's fix that as well. So Control H, find in files. We're going to look for f32 make, and we're going to replace it with make f32. So let's find all. And there's more there than I thought I would find. So that doesn't look nothing looks surprising there either. So f32 make, we're going to change it to mac f32 for make f32. Find in files. Make sure these still look correct. Good. And replace in files. Okay. Good. Now reload this. And now we can just do a quick sanity check and be like, hey, does that match? 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 And it looks good to me. So make float vec4. Is a vec4 a float vec? Yes, vecs are floats by default in Glsl code. That looks correct. Okay, what about make ivec2? ivec2, that looks good. Make u32, uint. Make int32, int. So the default of int is to be signed. Make float32. Float32 is just a float. And then we have this stuff here. Okay, awesome. So that looks good to me. We might want to edit our checksums here. It looks like when we were doing this, we lost track of that. So 1, 2, 3, 4, 5, 6, 7, and this is 8, and this is 9. And then let's add this as well. So this is 3 now. This is 4, 5, 6, 7. I don't know what's up with that. 8 and 9. So we got 9 of each, yeah? Or did we screw this up? So for some reason I see 8 here, but I see 9 here. That's a problem. And it looks to me like it's not... I did my checksum wrong, right? So let's look at this again. 1, 2, 3, 4, 5, 6. Oh, 7 and this is 8. Okay. There we go. So now we got 9 in the checksum. Awesome. Now the next thing is, can we rerun this project? Let's delete this shader. Oh, I am excited. We're actually getting somewhere. Let's rebuild this and see what we got here. Okay, so that looks good. We go over here, we get this thing, but once you press P for pattern, bam. Okay, ooh, this is, oh god, this is getting good. This is getting good. I'm getting excited. So this is good. This is awesome. This means that this Monday we're gonna make some. We're making we got serious stuff to start showing on screen. Awesome. So I do want to like figure out how to load a different default pattern into the editor so that we can test properly. But for now, I'm just like, I'm tired. Let's, screw this right now. Is really how I'm feeling right now. I think that if we really want a nice default pattern, we should try to make some type of function to generate something that looks nice, like some type of, I don't know, just some type of, we need some type of debug patterns that are very simple tile sets that just help give us some diagnostic information about what's going on. So for now, I'd say this is good for now. I just wanted to do something really quick to get some progress, because I was like, I know I just have to add a little bit more code to get something on screen. And I was right, which is surprising because usually it's like a lot more code. Git add dot get status git commit -am, and the vid IID is let's just say vid IID is 000118, and the time is 0 minutes 57 seconds and 57 minutes 30 seconds. P for awesome pattern, or actually you might want to say P key, because otherwise people are going to be kind of confused. That's still kind of confusing because you have to be in the PAINT5D editor for that even to work. But for now, that's good. Git status. Let's do a git push GitHub master. And then we'll push this up to kanji coder as well. But we're getting somewhere, like, and that actually looks kind of good. Like, let's git push kanji coder as well, because this build is actually working. And yeah, I'm really satisfied with my little Glsl build system here. Like, this is nice. We got something good. We got something good going here. After a whole bunch of programming, we're finally, right, it's like, the 118th video, and I finally feel like, hey, we're starting to get somewhere substantial. Like, all of it's starting to come together. So this is, also, I know my bit shift, I'm getting better at this bit shifting stuff. This is ridiculous, but I know exactly what this is crazy. This is crazy. Okay, anyways. That's enough for now. We'll do some more maybe later, but I just wanted to, I had this thought where I'm like, oh, it's just a little bit more code to get something interesting. The next thing we really want to focus on is making some type of default tile set for a single offset layer, so that we can debug this a little bit better. So that when we look at the shader code, when we look at that shader code for that pattern, I want it to be a relatively minimalistic pattern that gives me, that I can look at and I can verify certain aspects of things, right? So I think a few patterns would be nice if we could hard code some patterns into the. I think I might make some type of utility to hard code some bitmaps that are used to generate the patterns that I want. Yeah, I'll figure it out. So maybe like some type of ASCII tile map to bit-packed tile map utility would be a good thing for hard coding some of these tile maps, some of this data into the engine. So I think that's what I need to do. So actually, let's look at this. Let's look at our agenda. So the agenda screen. This agenda screen is getting huge. Glsl polyfill subsystem data only class. We just did that. Extend covpix to covbits to use bottom leftmost tile every time it sets its data. Right now, it's always using tile 0, 0 for every tile exponent size. So I know what that's talking about, kind of. I think it's talking about the test code. And we already thoroughly tested that, and we're kind of done with that. We're done with that. Make sure default pattern is uploaded to GPU. We did that. So 13 to 15 is done. 13 to 15 is done as far as I'm concerned. So let's look at this for a second. And let's kind of modify this a bit. So let's edit this list. So I'm saying 13 to 15 is done. But we're going to need a new 16. And we need a ASCII tile map to U32 byte array packer command line util to encode code default I'm going to come back to screen really quick. I just needed to edit this a bit. Okay, so we're going to change this around now. So here is our new list of what we're kind of working towards. We need a ASCII tile map to U32 byte array packer command line utility to encode default offset for debugging. So basically, if we try to make some type of tile map data that has, 120, like maps that have 128 by 128 pixels, the data gets way too big. So we want to, I think, just hard code something. Like, we want to come up with a set of patterns that we're going to use, and then just hard code it into like U32 values. We want to use we really just want binary patterns, right? We just want pure black-white bitmaps to encode into the source code as efficiently as possible, and we're never going to change these, right? It's just some type of default pattern that we need to pre-process and hard code into the code base. So we'll figure that out. I think that's what I want to figure out. I'll think more on that outside of the stream, but I think that, yeah, some type of utility for that is really going to help us. So I'm going to stop the stream, and maybe I'll be back later today, maybe I won't. But Monday looks like it's going to be promising. Like, we're actually going to make some serious headway. So later. Also, let's stop on here. So this was Glsl Visuals number 4, part 50 of the PAINT5D sprint. So I'm going to stop streaming.